All right, here you go, guys. 7.5. We're going to look at parts of similar triangles today. So the only objective we've got here for today is to recognize and use proportional relationships of corresponding angle bisectors, altitudes, and medians of similar triangles. So I'm going to remind you guys what all those words mean, and then we're going to talk about those theorems, and then we're just going to use them. So here we go. First of all, altitudes. An altitude, remember, is the distance from the base of a triangle to its opposite vertex. And remember that it has to meet at a right angle. So you'll notice on these altitudes there's the right angle sign there. And it's a line that goes straight down at a 90-degree angle from the vertex, the opposite vertex, to the base. Every triangle has 3 of them, depending on how the triangle is situated would tell you which of the altitudes to use here. Since the bases are CB and HG, that's where it starts and goes to the opposite side. But you could easily flip the triangle around and your base could become AB on this triangle, and maybe that would be your altitude. So it should be pretty clear on the homework because they'll have a right angle that just shows you the altitudes. But what is the deal with altitudes for today? Well, the first theorem, 7.8 here on altitudes, states this, that the length of the corresponding altitudes are proportional to the lengths of corresponding sides. Okay, so the best way to see this is to look at the example here. So if you look here, AD, okay, so let me just erase this so I can write over this. AD, which is an altitude of my first triangle, over the altitude of my second triangle, FJ, is equal to any side length. So they chose AB here. So this side length here, we'll do it in red, that guy over its corresponding part, FG. Okay, so that's super helpful in solving some of these triangles. That one's altitude. Let's look at the angle bisector. So if you have an angle bisector, which again cuts an angle exactly in half, okay, so that's different from an altitude. It doesn't necessarily meet at a 90 down here. There's no 90-degree angle marks. It's just cutting this whole angle into 2 equal parts. Okay, so if that's the case, it's called an angle bisector. And we know that the lengths of those angle bisectors are proportional to any corresponding side lengths. So notice here, looking at the example again, that helps us make the most sense of this. LP is this angle bisector over RT, which is this angle bisector. That relationship has to equal any of the corresponding side length relationships. They just showed one of them here. They showed, and I'll do this one in green, they showed LM in the first triangle, and its corresponding to the big one would be RS. Okay, so angle bisector distance over angle bisector distance equals side length over side length, as long as they're corresponding, right? So have to be corresponding. They have to be the similar looking side. All right, so lastly we have the medians. Remember that a median cuts any segment exactly into 2. A median's like another name for middle, and then connects to the opposite vertex. So here the lines CD and ZY, these guys, those are considered medians because they cut the side length in half and intersect the opposite angle. Notice it doesn't cut that angle necessarily into 2 equal parts or anything like that. Its only purpose is to cut the side length in half and connect to the opposite side. Opposite angle, I should say. So again, I'm going to look at this example, okay, because that helps me the most understand this. The example says that CD, which is a median, CD over the other median, YZ, has to equal any side length over its corresponding side length on the other triangle. So in this case, they used AB. Okay, so this distance over this distance. Okay, but it would have worked with any other one too, right? So if you wanted to change color here, just to be clear, we could say, AC over WY has to also equal that relationship. And then we can do yellow here, BC and YX would also have to follow that relationship. All right, so let's do an example with this. It says to find X here. So first of all, let's identify what's going on. Here we have that right angle sign. Okay, so which of the 3 things are we dealing with here? Well, we're dealing with, they all kind of have a similar relationship, but here it's an altitude, right? So these are altitudes. Okay, so the altitude theorem says that the altitude of and, we can call this triangle 1 and this triangle 2, just while we're talking about it. The altitude of triangle 1, which is 16, over the altitude of triangle 2, which is x, has to equal the corresponding side lengths. Well, the corresponding side length here, you'll notice k and x are congruent, right? So k and x, they have the congruent symbol. So we can see there that if we started with k on the first one and went to m, that would be the exact same as starting with x on the second triangle and going to y. Okay, so we would say those two sides are corresponding. So we can say, again, we have to start with triangle 1, so we would say 20 over 15. Okay, so that is the relationship between them. You can cross multiply here and solve, so you would get 20x is equal to 15 times 16, which is 240. So x then is equal to 12. And you are done with example 1. Part A, let's look at part B. This here would be an example of a median line because it cuts these side lengths exactly into 2. And then it looks like this angle here is congruent with this angle, and V is congruent to S, right? So that's what's going on with the angles there. So let's go ahead and do this one. So we have the median of 1 over the median of 2, that would be 13.5 over 9, equals, and we'll go corresponding side lengths. Since this is congruent to this piece x, I can actually use those, and those are corresponding. Since they're congruent to each other. So like if that's 3, then this is 3, right? So if that's x, this is x. So to simplify this, we could just compare x to 3. So if we do that here, we have triangle 1 would be x, triangle 2 would be 3. So that relationship, when you cross multiply, you get 9x is equal to, that comes out to 40.5. So then x would be equal to 4.5 when you do the math, and you're done with 1b. So you're just setting up these relationships and solving. Lastly here, we have the angle bisector theorem that says, if an angle bisector in a triangle separates the opposite side into 2 segments that are proportional to the lengths of the other 2 sides. So if you have an angle bisector, here that would be considered JM. If that is an angle bisector, then you can say that KM, which is this piece right here, over LM, okay, so it's the part that it's splitting, KM over LM has to equal KJ over LJ. All right, so that's the triangle angle bisector theorem 7.11. So let's use an example here to kind of show how that works. So for this one here, here's our angle bisector, and we know that because it cuts the angle into 2, congruent pieces. We can say that the different parts, they're basically are proportional. So we can say 4 over 6 equals x over 13. All right, so let's go ahead and do that. So we have 4 over 6 equals x over 13. When you cross multiply that, you end up with, you get 6x here equals, what does that come out to? 12, 13 times 4 is 12, 52. So then x would equal, it comes out to 8 2/3, and you're done. 3b, very similar, but notice we know the total length here. So if you wanted to know what this piece of it is, you'd have to do the total minus the other piece that you know. So this would become 20 minus x here, right? Okay, so we can say 11 over 14 is equal to 20 minus x over x. And then we can cross multiply here. When we do that, we get 11x is equal to 280 minus 14x. We move our x's over here, we get, let's see, what do we get? We get 25x equals 280. Therefore, x must equal 11.2. So again, just setting up the relationship that is proven in the theorem is all we're really doing today. I'll answer more questions in class. The homework, I should have a homework sheet for you, and we'll see you guys next time.